All right, I thought it might be useful to go over some problems in a separate video that I will also cover in a midterm review lecture in class, but I just want everybody to have additional time to study these things and sort of think about this at home. And so this is the same content we're going over in class. You can find additional midterm study material on the Canvas webpage, but I at least wanted to sort of have a video of this of what I will be covering in class. So just a few practice problems and sort of starting from this slide in the presentation that I gave in class. And so I started out with a practice problem like this where I could give you a causal loop diagram that you might not be very familiar with, and it might look very complex, and I might ask you to do things. So label, for example, links that are unlabeled. Now, unless you know a lot about clot formation, you might not be familiar with a lot of the terms that you see here. So, there's this word prothrombin activator and amount of thrombin and formation of fibrin fibers. And so a lot of these things you may not be familiar with, but the power of the causal loop diagram is if you had a domain expert at least draw the causal dependencies and you knew a little bit about the system, then you might actually be able to guess the direction of each one of these things. And once you actually have all of the polarities of the links, then you can then guess how the system is going to behave, even if you don't have any of that domain knowledge. And so we look at these things, we might look over and we see this size of initial cut or rupture, and it has apparently a dependency with trauma to local vessels. So trauma, I think I get that. So they're saying that if I get a cut, then there will be some trauma to blood vessels around that cut. And so if I increase the size of the cut, then I probably increase the trauma. So it seems like that's probably going to be a plus right there. And then this trauma, as it increases, well, there's this vascular spasm over here. Now, a vascular spasm, that's actually a phenomena where where your blood vessels constrict, and they constrict to reduce blood flow. And so if we think about this, well, trauma to local vessels, that will probably cause constriction in order to reduce blood flow. So as this increases, so does that. So that's probably also going to be a plus. Down here, even if you have no idea what a prothrombin activator is, we do sort of understand that we're modeling a wound healing, an immediate wound healing response. And so parts of your physiology are going to turn on after being activated by this initial cut. And so trauma is probably going to trigger that. And so it's probably a pretty good guess that this will also be a plus. And so you could keep going around this whole loop here, and some things will be pluses and some things will be minuses. For example, if the vascular spasm, as you increase the vascular spasm, so you increase the amount of blood vessels that are constricting, then you probably will decrease the size of the wound opening because there'll be less blood pressure, and so the wound opening will start to be able to close a little bit. The size of initial cut or rupture, though, as that increases, the size of wound increasing will increase, and so you'll actually be able to see that there'll be maybe a plus here and a minus here, and these two things will be kind of competing. So if we kept going along with this game, then we might end up labeling all of these things as such. And so a good exercise would be go through and see if all of these signs make sense to you. So as a blood clot forms, the size of the clot increases, the size of the wound will decrease. So that makes sense. So now that we have this giant diagram, then even if we don't know much about wound healing or the formation of these clots, we still can now understand or try to analyze the potential dynamics. So we're going to label the loops. So if I look closely here, I've got a loop going from size of wound opening to formation of fibrin fibers to size of the clot back to size of the wound opening. So this here looks like it's a negative feedback loop. So as the wound gets bigger, there's more of these fibrin fibers that form. As the fibrin fibers form, the clot gets bigger. As the clot gets bigger, the wound decreases. All right, now, so are there other loops that we're missing out on here? This down here looks like a loop. So as the size of the clot increases, the amount of thrombin looks like it increases, which also increases the amount of these fibrin fibers. So I don't need to know what thrombin are or fibrin fibers are, but to know that this is a positive feedback loop. So I might only understand this size of the clot. And I can see that as the clot gets bigger, there is a process that will make the clot even bigger. So there is a growth loop here, but this doesn't go on forever because as the clot gets very big, eventually it closes the wound, and as the wound closes, these fibers stop forming, and so there's a negative feedback loop. If I look around, I don't see any other loops because everything kind of radiates out. And so I think those are the only two loops. And so I end up seeing that I have a reinforcing loop that is adjacent to a balancing loop. And they both kind of play a role in the size of the clot. And so the size of the clot will grow, and then it eventually will level off. So I would expect I could call this a limits to success example, or I could just call this S-shaped growth. So if I pick any variable participating in either of these two loops, they're either going to have an S shape where they're going to, let me see if I can actually maybe draw this. So I'll pick a pin here. So I'm either going to have S-shaped growth that's going to look like this, where they start small and get large, or I might have S-shaped growth that looks like the mirror image of that, where it starts large and gets small. So like the size of the wound opening will start large and it will get small, but the size of the clot will start small and get large. But we consider both of these to be S-shaped growth. So if I asked you to plot your guess as to what each one of these things would look like, then you know that you probably wanted to plot it to look like one of these two curves, and then you have to kind of guess as to which curve would be most appropriate. All right. Another thing that I could ask you is I might show you different simulation outputs for different values of dt, and then you'll have to choose a good value for dt, or the time step for that simulation. So I might show you, for example, these 6 plots. These all are the same simulation of, let's just say, bacterial growth. But this top plot in the top left, this one is for dt of 0.1. Let me see if I can change my pointer here to maybe a laser pointer. All right, so this top one is 0.1. This next one is 0.05, so it got smaller. It gets even smaller, 0.005, 0.001, 0.0005. And so if you look through this, you notice that these 3 plots are slightly changing. So they all have the same axis, they all go to 500, but this blue growth line, it only hits 300 at 6 seconds. Here it hits 350. Here it almost hits 400. Here it gets almost to 400, but it's a little closer to 400 than this one, but it is not that much closer than, there's a lot, it's not as different as these 2 plots. And then we get even closer to 400, and by the time we go from here to here, I can't tell a difference between these 2 plots. And so I would say that probably the right dt would be somewhere in the neighborhood of this one and this one. And I might lean towards this one because it sort of seems the most like everything after it, whereas I can still see a little bit of daylight between this one and this one. So it seems like all 3 of these have converged on the same shape, and I want to choose the dt that is as large as possible, but still gives me roughly the same shape. And so I'm saying that that is the ideal dt. So there's no significant changes in plot for any dt smaller than that, so that's a good choice. Now you have to be very careful when I give you problems like this, because you have to look to make sure that the scale is properly accounted for in your analysis. So notice that in this case, I've got 6 plots just like before, but sometimes this is scaled to 350, then this goes to 400, and it says 400 here, then this goes to 450, and then this goes to 450. So when I look across here, it looks like there's a major change from this one to this one, and it looks like there's a minor change from this one to this one. But in reality, the scale totally changed from 350 to 400, and so these 2 are actually very different plots. Whereas in here, the scale changed, and even though the plots are actually very similar, because they're plotted on different axes, they look very different. And this is a common problem because unless you manually adjust your plots, a tool like Vensim is just going to choose a scale for you. And so it's important that before you decide that something's converging to the same shape, you make sure you didn't accidentally get tricked by a change in scale as you go from one DT to the next. So be careful about axis scaling when looking at these things. All right, so I really like this problem. So stock and a very, very simple stock and flow is given here, where I have a stock of bees in a hive. So this could be any stock. And it has an inflow, in this case, bees entering the hive. So it's a rate of bees entering the hive, and this is a rate of bees leaving the hive. And then in this plot over here, it's been plotted in Stella, this solid gray line is the bees entering the hive, and this dashed dotted line is the bees leaving the hive. And we notice that there's a period when the entering the hive is larger than the leaving the hive, and then a period when the leaving the hive is larger than the entering the hive. And so we have to, if we think this through, then we can think the net flow in this period where the entering is greater than the leaving must be positive. So even though the entering peaks and comes back down, there's always bees in the net number of bees is increasing during this period up until this time. After this time, regardless of what's happening with the individual curves, it's always the case that the leaving number is higher than the entering number. So there's never enough bees to replenish the ones leaving the hive. And so you get growth in this period, and you get decline in this period. So the maximum number of bees in the hive must be right here when the inflow rate is equal to the outflow rate. And that actually makes a lot of sense if we think of this kind of from a calculus point of view, because if we plotted the number of bees in the hive, and we took the derivative and set it equal to 0, then that would give us the point at the top of this point, and that would be where the flow, or where the net flow, so the rate of change of the beehive, is equal to 0. And that happens when the inflow rate is precisely equal to the outflow rate, which is where these two lines cross. And so this is us just regenerating a classic result from calculus that in order to find out where the maximum is, you take the point of tangency such that with a line of slope 0. And so you find a flat line and you bring it down to the curve and find out where it goes tangent to the curve, and that is identical to saying you find where the inflow is equal to the outflow. And there you have it. So at time 14, that's when you have the most number of bees in the hive. All right. So I might also show you a stock and flow and ask you to put formulas on here. So if before I put some formulas up, I would say think about units. So in the population number here, it looks like just based on things I see females, fraction female, mature females, births per mature females. So I see a lot of females here, so I'm guessing this then is a stock and flow model modeling the number of females in a population. And so there's a death rate, and so you can see that the number of females, for each female, has an average lifetime, and then those two go together to get a death rate. And then for each female, so I see females, it looks like, so this population must be not just females, so this is the whole population. So there's a fraction female, so this converter down here, this is the number of females, and so this is just the total number of the population. And so they would say, well, what fraction? So where you might assume like a 50% fraction. So this is the fraction that are females. And then we then say, all right, well then, so what fraction of those females are biologically mature? So this is some other fraction, let's say 25%. And then that gives mature females, and then those are the only ones that can potentially give birth. And so then they say, well then, so for every mature female, what is the rate of birth? And so how many births does each mature female have per year? And so you might have non-reproducing females and you might have reproducing females, but you average them all out, and you'd say that okay, for all of the mature females, if only one of them gives birth in a year. So let's say one female out of 10 gives birth, and she gives birth to one offspring in that year. Then we would maybe say this is zero point 0.1 births per mature female per year. And then that will go into birth. So we've looked at this, so we roughly understand what's going on here, and now we want to figure out what the formulas might be. Well, fraction female, if I have a population, that would be P, and then P times the fraction female should give us the number of females. So that's one example. So I'm going to uncover some of these formulas and say, all right, so I just put labels on all the dynamic variables, P, B, R, etc. And then I can then set up these formulas that then relate all of these things together. So if P is the stock, the current number of population, and if F is the number of females and lowercase p is the fraction, then the formula here is just going to be P times P. So this fraction female, if you're to think of the units, that might be females, females per, females per individual or something like that, or probably, it'd be some unit conversion that converts a generic individual into females. So you can say what slice here. So this might be 50%, and these are individuals. And so what comes out of here, this converter, are not just individuals but females. And so P times P gives us the female number here. So then how many mature females? Well, similar math goes on here. So what fraction of F is equal to mature females? Well, that's just going to be F times Q. Okay, so now I have the mature females, and I have, for each mature female, how many offspring does she have in a year? Well, so the birth rate will be all the mature females times the rate of offspring production per female, and so B equals N times R. And then that goes into the flow. So the only other formula we're left with is the death rate. And this is a familiar one from the bacterial example. So this has nothing to do with females. It's just in general, the average lifetime of every individual in the population is L. And so P divided by L gives us the death rate out. So be able to look at a relatively simple stock and flow diagram like this, try to get an idea of what's going on, and then make some guesses about these things. And worst comes to worst, you can always check the units. So here, these are individuals divided by time. Well, that individuals divided by time, individuals per year, yeah, that's a rate. That's what we want. This is births per mature female per year, multiplied by mature females. Well, that will cause the mature females to cancel, and so we end up getting births per year. Well, that's a rate. That's what we want going into there, and so on. All right, next problem. So I can give you something more abstract like this ratio, where I say z is equal to x divided by y, and I want you to draw a causal loop diagram representing this relationship between z, x, and y. So what might that look like? Well, I know that z depends on x and y, but x and y do not depend on z. So I draw these causal links, x, z, that represents that z depends on x, y, z, z depends on y. And I know that if I increase x, then I will end up getting an increase in z. So I put a plus on that. And if I increase y, because it divides x, I'll get a decrease in z. So I'll put a minus. All right, so let's make things more complicated. What if I add a second equation? A is equal to y minus z. So now a depends on z. A also depends on y, and z still depends on y. So I can take the causal loop that I already had, which is this thing up here, and then I can add an a out here and then add some links. And so from this formula over here, I know that a depends on y, so I draw this y down here, and I know that if I increase y, I will also increase a, so I put a plus there. I also can see that a depends on z, so I draw this line down here. If I increase z, because I will subtract away from y, then I will decrease a. So I put a minus there. And there's the causal loop. It represents those two equations simultaneously. All right, so probably a little more complicated here, and let's do a differential equation. So we know that a differential equation and a stock and flow diagram, that a stock and flow diagram is a representation of a differential equation. So we should be able to take a differential equation and turn it in to a stock and flow diagram. And then when we have that stock and flow diagram, we should be able to then generate causal loops out of it. So let's see how to do that. Well, whenever you see a dA dt, dB dt, or dC dt, the things that are next to the d in the numerator here are your state variables. They are the stocks. So since I have a dA dt, I need an A stock. Since I have a dB dt, I need a B stock. And since I have a dC dt, I need a C stock. Now, when you look at these things, you have different ways in which you can write the inflows and outflows as it seems convenient. So for this A, I just see that I have both positive terms here. So I could just say this is one big inflow that depends positively on both B and C. So over on A, I just draw one big inflow. And then I can draw these causal links. It depends on C and depends on B. And if I get to annotating them, I might put pluses there. But remember, a simple pure stock and flow diagram does not need annotations on the links. So then, I then look down and I say, all right, dB dt. Well, this one is a purely negative right-hand side of the equation. So that means that rather than drawing an inflow and saying there's a negative relation to the inflow, I can, for convenience, draw an outflow, and outflows are implicitly negative. And so this outflow depends upon C. And so we'll get to this in a second, but it'll actually depend positively on C, even though there's a negative there. The negative is already taken up in the fact that this is an outflow. So I draw an outflow because I see this as negative, and then I say that the outflow magnitude depends upon C. And then C, like A, is a simple inflow because it's positive here, so I can draw an inflow going into C, and then I can say it depends upon B. So that is a representation of the little differential equation system that I've drawn that I've written in the upper left-hand corner. All right, so let's say I want to annotate those. Well, here are those annotations. So again, I have a plus going, so this plus might make sense to you. The inflow going into A depends positively on B and C. The inflow going into C depends positively on B. Those come right out of these equations up here. So the inflow, this is the net inflow. That's a way you can think of the rate of change of A or the derivative of A. You can think of it as the net inflow. It's B plus C. The net inflow into C is just B. And then this here, dB dt, the way it's drawn, that negative is implemented as the fact that this is an outflow. As a consequence, we don't have to represent a negative here because the negative is implied in the fact that this is an outflow. So there is an implicit causal link going back from the flow into the stock, and that there is represented by this negative here and vice versa. So because the negative is already there, then this is actually a positive link because this flow here is sort of the magnitude of the outflow. The fact that it is an outflow is what's already doing the business of this negative sign. So going back, whenever you see a negative there, we can represent it as an outflow. And once it's represented as an outflow, the negative's already taken care of, and so everything after the negative you can think of as positive. All right. So that's all I'm saying there, is that this implicit backward link corresponds to this negative right here. And so if I look at this, I can see that there is a loop here. So there's an implicit positive link going this way. And so I get a negative feedback loop here. And so this is our stock and flow diagram with links and loops labeled. So this isn't a causal loop diagram. This is just an annotated stock and flow diagram. If I just ask you for a stock and flow diagram and don't ask you to annotate the links, then you don't have to worry about doing that. Now, if I asked you to generate a causal loop diagram, so if I were to go back to this, and these flows might have names in reality. So this flow out of B could say birth rate. or out of C you could say death rate or something like that. So they could already be labeled. But if they're not labeled, they're just depicted here symbolically, they still are dynamic variables, so I need to give them a name. So if I wanted to turn this into a causal loop diagram, then I know that some of my dynamic variables are going to be A, B, and C, but these flows are also important dynamic variables. So I'm going to just name this one flow into A, name this one flow out of B, and name this one flow into C. So now I have 6 dynamic variables: A, flow into A; B, flow into B; flow out of B; C, flow into C. And I can just write those 6 dynamic variables down and then draw their causal dependencies. And that's what I have here. So there's A, flow into A. So I know that if the flow into A increases, so will A. I know if the flow into C increases, so will C. I know if the flow out of B increases, then B will decrease. And so that's why this is a negative there. And then the rest of these links are effectively the links I've already drawn. So based on the formula that's up here, I know that the flow into A, that's dA dt, depends positively on B and C. So there's a B link, and there's the C link. I know the flow out of B, so that's like dB dt equals negative. So the negative is included in the out of there. And so, so the flow out of B depends positively on C. So this link, this big link around the bottom here, is positive because the negative is already taken care of with this one over here. And then the flow into C depends positively on B. So that's what's going on there. So then I do see that same negative feedback loop here and no other loops. So that's my causal loop diagram. So I could give you these 3 equations and just ask you to write a causal loop diagram without the stock and flow diagram, in which case you could name these flow out of B, flow into A, flow into C. If you wanted to, you could even just put dA dt here, dC dt here. Now if you put dB dt here, then this would be positive, and this one around here would be negative. But because I use the term out of, it's like I put kind of that sort of switched which one of these got the negative. Okay. So that's what I'm saying here. I could have said flow into B, which would be the same as saying dB dt, but then these connected links here and here would have to flip their signs. And those are the practice problems that I will present in class. And so if you have any other questions, then feel free to send me an email or the TA, or come to office hours, etc. Again, there are additional videos and resources online to help you study for the midterm, including a practice midterm, a practice problem set, which has another auxiliary video which goes over the solutions to it. So I hope that's helpful. Again, feel free to get in touch if you have any future or any further questions.